Hey guys, today we are going to take a look at uniform distributions. So this is the first of several different probability distributions that we're going to talk about. Now before we talk about that, we do need to define some terms here. So first of all, we're looking at probability experiments that have numeric outcomes right now. In other words, these are outcomes that can be counted or measured. So they're just, the outcome is a number, in other words. So there's two types of these. There's discrete and continuous. So discrete variables are numbers that have a finite amount, okay? So numbers, try that again. Numbers with a finite amount. A finite amount. Okay. Usually these are whole numbers. Okay. Usually whole numbers. And so what I mean by this is you can't have decimals, or typically you can't have decimals. There's a set possibility. I always talk about the volume knob. If you've got a discrete volume knob, it clicks. Okay, you're either on one setting or the next setting. You're not in between. You can't scale in between them. There's a set number of these possible outcomes that you can have. The only exception to it may be not the only exception, but the most obvious exception for this whole number system, because it's things like how many siblings do you have or something like that. Well, you can't have a fraction of a person, even if they are a half sibling, I suppose, but that doesn't count. It's a person, okay? But the exception to the whole no decimals is money. Okay, money is a discrete variable, and that's because you can't have part of a cent. Okay, so even though we can have two decimal places, it could be $3.23. You can't go any further than that because we do only deal in cents. Okay. Continuous variables are sort of the opposite here. So these are the ones where you can have a never-ending decimal, okay? So I'm just going to write exactly that. Can have never-ending decimals. So again, going back to the volume knob, if you have a continuous volume knob, it means that it's a smooth volume knob that you can put it exactly where you want. Okay, so for instance here, we could have height or weight, any distance or anything like that. So we'll just go height and weight. And so the idea here is that no two people are going to be exactly the same height. One person's taller and one person's shorter. It's just how accurately do you want to measure, right? So if your measurement tool goes to 1 billion decimal places, then you can measure it to 1 billion decimal places. You could go even further. It's just usually we don't measure that accurately. Okay, so we're going to classify these as continuous or discrete. So first of all, the number of phone calls made by a salesperson. So that's going to be discrete. You can't make part of it a phone call. You either made the call or you didn't make the call. So the length of time they spend on the phone, however, that's going to be continuous, because even though we usually only measure by second, we could measure by millisecond, microsecond, whatever. You can go as accurately as you want. Okay, a company's annual sale, well, we already talked about how money is discrete because you can only deal in cents. And the distance from the Earth to the Sun is going to be continuous because it's how accurately do you want to measure it. Okay. All right, so we're going to talk about this uniform probability distribution. So what this means is all outcomes in this distribution are equally likely in a single trial, and the sum of the probabilities has to add up to 1. So what we're going to have is basically, if every outcome is equally likely and nothing has the advantage here, then the probability of n(x) is going to just be 1 over n, where n is the number of outcomes. Where n is the number of outcomes. That's an m. All right. So examples here would be flipping a coin or rolling a die. Okay, flipping a coin, rolling a die. Okay, you roll a die, every face has exactly the same likelihood. Okay, there's 6 sides to the die, so the probability of rolling a 2 is just 1 out of 6. The probability of rolling a 4 is 1 out of 6. Similarly, with flipping a coin, there's 2 outcomes, equally likely. So heads is 1/2, tails is 1/2. Okay. All right, so let's move on to a slightly different sort of distribution here, kind of very related, but maybe not as obvious. This is the, certainly this one right here, we'll even put a star here. Let's use blue. This one right here, this is your casino one. This is what you're going to want to use for your casino project, because this is going to tell you the likelihood of, well, whatever, you'll see. Okay, so anyway, so the expected value, this means like what do we expect to happen, okay? And so for the expected value for a discrete variable like this, just a set number variable here, we usually write it as a big E x, okay? And what you do is you take the numeric, because we're getting numbers as answers here, we take the first number, okay? Whatever that number is, we'll call it x1, okay? That's the possible outcome. And you're going to multiply it by the probability of that outcome, okay? If you continue with this, if we then say, okay, well then let's add the second outcome times the probability of the second outcome, and then we just continue like that. So for every outcome, you just multiply the actual numeric outcome by the probability of that outcome. That's going to give us what we expect to happen. Doesn't mean it will happen, it's what we expect to happen. It is also worth mentioning that it's a theoretical value, and so sometimes the answer is impossible, especially some of the later distributions we'll look at. A lot of the times what we expect to happen is not actually possible. It's just a theoretical idea here. So this is where n is the number of outcomes in this case. The number of outcomes. All right. So what else and I got to define so xi, we didn't write any i's here. I wrote 1, 2, and 3s because that's the idea. It's just a number that changes. So this is the random variable. Random variable. So for instance, if I was talking about rolling a die, this here would be the 1, the 2, the 3, the 4, the 5, and the 6. Okay, those would be your 6 possible outcomes. And you just multiply by the likelihood of each of those. Okay, the p of xi is the probability of xi. Of xi. Okay, and that's that. So let's put it to use. There we go. Okay, so let's look at an example here, and so we'll talk about the lottery. And this is where you'll see that this is how this relates to your casino game. This is what you're going to want to do. So first of all, hold on, sorry, I got my answers all mixed up here. I've lost my answers. I did them ahead of time, so I wouldn't do this. All right, so the first thing here, we're considering a simple game where we roll a single die. Okay, if we roll an even number, you gain that number, and if you roll an odd number, you lose that number. Okay, so for what can happen? So if you roll a 2, a 3, or a 2, a 4, or 6, you just gain that many points. 2, 4, or 6. If you roll a 1, 3, or 5, you lose that many. So those would be negative values. Okay. Now the probability for each one is just going to be 1 out of 6. Okay. So if we were to graph this distribution, and this one's really straightforward, and it seems kind of like a waste of time to graph this, but as we do more distributions, the graphs will tell you a lot more. So anyway, so we'd have -5, -3. This is all the possible point outcomes. Okay, each one is going to have exactly the same probability. They're all 1/6, and this is why it's called uniform. Okay, in this case, they're all exactly the same likelihood, so it gives us this uniform shape, this straight line here. Okay, oh, and that's points. You will not need to, I won't ever make you graph a distribution, but it is, well, like I say, this one's kind of boring and doesn't really tell you anything, but we will do ones where it tells you quite a bit. Okay, so to find the expected, so let's find out what do we expect to happen. That's what I mean by expected value. What do I expect to happen every time I play the game, every time I roll that die? And so you're going to take the -1, you're going to multiply by the probability of that happening. Okay, we could gain 2 points, and the probability of that one is also 1/6. We could lose 3 points, probability of that is 1/6, and so on. So we just go through, gain 4 points, again multiplying by the probability of it happening, lose 5 times the probability, and we could gain 6 by the probability. Okay. Now, you will notice, and a lot of the times this is the case, if you're dealing with these probabilities, especially if it's uniform and the probability is the same, what we can do is we can actually just add up all of these on top. -3 plus 4 minus 5 plus 6, and divide the whole shebang by 6. Okay? And that will give us 3 out of 6. Okay? Which of course is just equal to 1/2. So what we expect, hold on, I'll give myself some more room here. So what we expect, I don't know why I stayed using the blue. Sutton blue, okay. Yeah, so every time we play the game, we expect to gain 1/2 point, which of course is just like I said earlier, you can't go up. Like, it's impossible in this game to gain 1/2 point. You can't do that. But that doesn't matter. We expect to go up 1/2 point every time we play. And that's, again, it's just a theoretical thing, okay? Now this is an important question, this one. It comes up on tests all the time. And is it fair? What does it mean for a game to be fair? Well, the game is not fair, okay? Because for a fair game, the expected value is 0, okay? For fair games, the expected value is 0. We expect, on average, for everything to sort of cancel out, and you're just as likely to come out on top. This game, we were more likely to move ahead every time we played, which, of course, it's a pretty boring game to have a fair game, unless it's gambling or something like that, I suppose. But no, usually games are not fair because we want to progress the game. Oh, and I already said this. So this is 0. Okay, so the expected outcome of a fair game is 0, and that's what it means to be a fair game. That's the definition of a fair game. Okay. All right, so which die has a higher expectation? So we've got a 4-sided die that has 6, 12, 18, and 24 on it, or we've got a 6-sided one that has 4, 8, 12, 16, 20, and 24. So the question is, which one do we expect to give us a higher number? And like, you can look, and they're pretty close, so it's very difficult to just say by looking at it. So what we're going to do is we're going to write out sort of the distribution here. So we make a chart, okay? And for each, we make a list of all the possible outcomes. So for the first one, we got 6, 12, 18, and 24. Okay? The likelihood of each of these is 1 out of 4. There's 4 possible outcomes, equal likelihood for each. So that's for A. That's A. And then we'll go over here and we'll do B. Okay, B, same idea, except this time we've got 4, 8, 12, 16, 20, and 24. And the probability of each of these, again, it's a uniform distribution. Everything is equally likely. So this time there's 6 possible sides. Okay, so it's going to be 1 out of 6. All right, so let's go do the first one. Or do A first, find out the expected value, because this one's going to be faster because it's shorter. So we've got 6 times 1/4. Okay, again, we've got the outcome and we've got the probability of that outcome, and you're just multiplying them, and you're going to do that for every single one and add them up. So 12 times 1/4, and then 18 times 1/4. Okay, plus 24 times 1/4. And again, because it's uniform, I can sort of cheat this, and I can just say, well, then that's 6 plus 12 plus 18 plus 24, all divided by 4. Okay, and that works out to be 60 over 4, which equals 15. Okay, so we expect to roll a 15 on this die, which again, I know I'm going to keep saying this all unit. Expected value doesn't have to make sense. You can't roll a 15 on this die, but that is what we expect to happen. Okay, so we'll go do B here, and the process is exactly the same. Okay, we've got, let me zoom in here. It's easy. I zoom in and it looks a little neater. So I got 4. This time they're all times 1/6. So we got 4, we got 8, we've got 12, 16, 20. Oh, I'm running out of room. And 24. Okay. No, I wasn't. Okay. 4 plus 8 plus 12 plus 18. Oh, no, I missed one, didn't I? 16. 16 plus 18 plus 20 plus 24. And we divide the whole thing by 6. And that will give us 84 divided by 6. You're welcome to check my math if you want, but I'm pretty sure I'm right. And that equals 14. So we expect to roll a 14 on that die. So which one has a higher expected value? Well, that would be number A. So dice A has a higher expected value. Okay, that's it. So there is another page of question here. It's just one giant question. And what I want you to do is I want you to take a look at it. And that is how we're going to start tomorrow's class. So until next time, go Sabres.